So I'm Adib Rastegarnia from Purdue University. Today I'm going to talk about a gRPC-based event distribution system that I developed as an ONF application to explore the feasibility of migrating from a monolithic architecture to a microservice-based architecture. So for sure, next generation of ONFs is trying to address the problems that I'm going to talk about properly and fundamentally. But for 10 to 13 minutes, forget about macro ONFs, and let's see that how can we solve these problems with current version of ONFs. So as you may know, most of the SDN controllers have been implemented based on a monolithic architecture. It means that all of the PCs, services, application integrated into one single huge program. And even if you don't need all of them, you still need to build all of them together. And there is no easy way to take some of the pieces out of the SDN controller and minimize it to, for example, a few components. The components that you really need. For example, in the current version of ONF, we have more than 100 applications built in. So typically, as a PhD student, I use typically a few of them, right? So I don't need to use all of them, but I still need to build all of them together. So, and this is one problem. Another problem is the lack of uniform set of northbound APIs. So I use different SDN controllers. So when I started working on SDN since 2014, I started working with Open Daylight. So, and then I migrated to ONOS, I work with Rio. One of the problems that I encountered with is that most of these SDN controllers provide REST API as a northbound interface, but typically in terms of functionality, most of them provide the same sort of functionality. They provide topology information, we can install and remove flow rules, all of this stuff. Some of them have some features like WebSocket that we can receive events, but the problem is that the naming convention, the syntax that they use are different. For example, I remember that 5 years ago, we wrote an application, more than 3,000 lines of code in C++ as an external app using Open Daylight to implement an SDN application. So can we use that application with current version of ONOS? Oh, no. Why? Because we still need to recode some of the modules that we wrote to retrieve topology information and install flow rules, all of this stuff, right? So this is another problem, lack of uniform set of northbound API. And again, lack of usability of software modules. For example, if they provide a REST API, we need to parse JSON or XML inputs, right, to the program and then put it into appropriate data structure in C, C++, Go, or any programming language, right? So some of these modules can be reused in different programs, in different SDN controllers, right? So, but we don't have this option now. And lack of scalability and reliability. Because of strong dependencies between these pieces, sometimes strong dependencies between applications and some of the services. So if one of the applications doesn't work properly or some of the services have some bugs, so it's likely affect other services, other applications. So it happened to me a lot that sometimes a service or an application fails and then the whole SDN controller is down. So these kind of problems I encountered with. So what's the solution? The solution is that we need to migrate to microservice architecture. So it means that the controller should be reduced to a set of minimum control components, that these components are microservices, they communicate with a standard APIs, programming language agnostic APIs like gRPC, and the rest of the stuff should be implemented outside of the core. So as an external application or as an external services, right? The core of the controller should be minimal. So, and we should be able to pick any of these services, put them together, and we have a fully functional SDN controller. So we don't need to build in all of this stuff together. So, and next generation of ONOS is trying to address this problem fundamentally. But, so what are the advantages of disaggregating the control plane services? One of them is the flexibility to scale. Each of these subsystems can be scaled independent of the other subsystems. So another thing is freedom in choosing the programming language. As a developer, I would like to choose my programming language, right? So I don't want to stick to one specific programming language. That's the reason that most of the applications that I develop for the SDN stuff, so I use the northbound interfaces, that I have this flexibility to choose any programming language that I want to develop that application, right? We should give this freedom to the programmers to choose whatever they want to. So any programming language, any third-party libraries. So, and migrating to a microservice architecture gives this opportunity to programmers to choose whatever they want. Fault isolation, so typically if one of the subsystems fails, it doesn't affect the execution of other microservices. Minimal built-in components, so typically an SDN controller should provide the minimum set of components that we need, right? The control side, configuration, and then operation. And the rest of the stuff should be implemented on demand. So if you would like to implement your application, you can do it yourself. So it shouldn't be part of the SDN controller and a disaggregated code base, right? Each of these subsystems can be in a separate repo, and they can be developed independent of the other subsystems, right? This is another opportunity for the developers to focus on one specific subsystem. Okay, so for this project, I work with David Bembry. Probably some of you guys know him. So last year, he presented in Open Networking Summit, something like this. So this is one way to look at the control plane disaggregation. What's the idea? The idea is that we can have a minimum set of control components, including a set of southbound protocols. These southbound protocols, OpenFlow or any other southbound protocols, communicate with the devices, and they receive messages, events from the network devices. And there is an event distribution system, part of this controller component, that is responsible to externalize the event processing to the external processes, right? In my opinion, the most important aspect of an SDN controller is processing of these events, right? Look at the current version of ONF. Event processing is one of the key pieces of the current version of ONF, right? We have link events, we have network topology events, right? Device events, packet events, right? So if we can externalize these events, we will be able to implement most of the services and apps outside of the core. Think about this. Let me give you an example of that. What is the topology discovery? So it's nothing more than receiving the LLDP and R packets and then process them and then build a network topology based on that, right? So if we can externalize packet processing, right, we will be able to implement the topology management service outside of the core, right? So let me give you another example. Reactive-based application, reactive forwarding. What it does, so it receives the incoming packets, process it, install flow rules, and then return the packet to the pipeline, right? So if we can externalize packet processing, we can implement reactive-based application outside of the core, right? So, so that's the reason that event distribution system is one of the key components of the control plane disaggregation. If you have an event distribution system, we can implement most of these services and then application outside of the controller code. So I explored two event distribution systems based on two technologies. One based on Apache Kafka, which is, in general, it's a publish-subscribe model. That means that we publish events to a cluster, Kafka cluster, and then the consumers consume the events from the Kafka cluster. Another approach that I use a point-to-point model using gRPC as a technology, so to implement an event distribution system. So this is an event distribution system based on Kafka. So what it does, we externalize event processing using a Kafka-based event distribution system. The Kafka event-based event distribution system publishes the events to the Kafka cluster, and the consumer consumes the events from the Kafka cluster. So Personally, I don't like this approach. I would prefer to use gRPC. One of the reasons, at least as a developer, what I found out, I found gRPC is easy to implement. So a gRPC-based event distribution system. In this case, for example, if you use Java or Go, you need to implement a minimum set of helper functions to implement consumers, right? Another problem is that there are lots of parameters in Kafka, and you need to tune these parameters if you would like to get a good performance out of it. So, and there is no easy way to find that, okay, what is the best parameters? So, and it's really environment dependent. So, another model is the gRPC-based event distribution system. So, we don't need to have a Kafka cluster to put it there. We can use a point-to-point channel. So, and then using the streaming, server-side streaming in the gRPC to publish the events to the subscribers, to the app and the services. So, if you look at in these both of these models, okay, so we can externalize event processing, right? Think about the packet processing. If we can externalize packet processing, it's good. So we can implement reactive-based applications, we can implement some of these services, but we need a mechanism to return the packet back to the pipeline as well, right? So the packet out. So I also implemented a gRPC API to return the packet back to the pipeline. So I use the ONF REST API for installing flow rules, all of this stuff, but I implemented a gRPC API to return the packet back to the pipeline. So to close this loop, right? So just processing the packet is not enough. We need a mechanism to return the packet back to the pipeline. So why I was doing all of this stuff? So I was working on a project called Umbrella. So, and I was tired of implementing one application for one SDN controller and then recode everything for another SDN controller. I decided to implement a framework that I can write one single application that I can execute it on multiple SDN controllers. So this project that I implemented is a framework that you can write one single application and you can execute this application on ONOS, Open Daylight, and Rio SDN controllers. So the idea is that all of these SDN controllers provide northbound APIs. So they provide topology information, you can install flow rules, all of this stuff, right? What we need a set of drivers. These drivers are responsible to translate a unified API, which is the Umbrella API. It provides flow service API, topology API, to the northbound API requests from the different SDN controllers, right? So what was the problem? The problem was that typically northbound APIs have been designed for proactive-based applications, right? So there was no mechanism to provide packet-in messages to the external processes to implement reactive-based application. So it had a missing part. What was the missing part? The missing part was the event distribution system. So I equipped this framework to an event distribution system, and then I was able to implement reactive and proactive-based application completely outside of the controller code. So it means that I can use Umbrella API to implement a reactive or proactive-based application completely outside of the code of the controller. So this is one use case of migrating from a monolithic architecture to a microservice architecture. So I also had some experimental results. Probably it will be interesting for you. So, and you will see that why I don't like the model of the Kafka because of this. So event distribution system is a good thing, but it has consequences. Adding one layer that externalizes event processing, so it has some consequences. What is the consequences? Performance. So we are adding delay. So the question is that if this delay is negligible or not. So can we ignore it or not? So the first scenario is that suppose that we have two endpoints. We are sending packets to each of the switches. These switches, suppose that we don't want to install rules. We want to see that what is the end-to-end response time if you send the packet, each switch send it to the controller, return it back to the switch, and send it back to the another switch. Goes down until it reaches to the destination, right? We would like to see that what is the response time if we use ONOS, the current version of ONOS, if we use the gRPC event distribution system to do that, or a Kafka. So if you use current version of ONOS, an end-to-end response time. So all of these experimental results have been done on a physical testbed at Purdue University, which has 10 OpenFlow switches, logically defined 50 switches, and more than 130 links. So for a 5 hops end-to-end thing, so if you use current version of ONOS, we can see that the average response time for a ping is 24 milliseconds, right? If you use gRPC, so it goes up to 29 milliseconds. So, and for the Kafka is 35 milliseconds. So I think for gRPC is close. So in terms of flexibility that we get out of it, so I think that it's good enough. So, but there is a delay. Yes, you have a question.
Do you think the delay will linearly scale as you increase the...
Exactly. Yeah, as you increase the number of hops, the delay will be increased, right? So typically, I think less than 1 millisecond is delay added per hop, less than 1 millisecond. So it means that as you increase the number of hops, so you will see that the delay will be more.
Does it also depend on the amount of traffic that you send through, like number of concurrent?
I don't think so, but typically, if you try to overwhelm the controller, so I think that even the controller cannot handle that. So the software cannot handle that. So it's not just the controller. But typically, the first incoming packet is important. Think about the reactive-based application, right? We want to process the first incoming packet and then return the packet back and install flow rules, and then we are done, right? We don't want to keep processing the incoming packets, right? So I don't think it's really dependent to the amount of traffic that we are sending. Another thing is the throughput. And so again, for this, I use 2 APIs. One API, the REST API for installing flow rules, and gRPC for sending back the packet out to the pipeline. So in terms of throughput, so, okay, for sure, ONOS has a better performance. The reason is that ONOS doesn't use the REST API for installing flow rules. REST API is slow for installing flow rules when compared with the internal APIs that we have in ONOS, right? So, but even based on this assumption, I think that the throughput also is good enough. It's you will see that the difference is around 20 to 40 megabit per second for a 1 gig link. So, and I'm pretty sure it's not because of the event distribution system, it's because of the mechanism that we use for installing flow rules. So if you replace REST API with gRPC for installing flow rules, you will see that, okay, you will get the same or almost the same throughput that we are getting with current version of ONOS. This is, as you can see, I tested with ONOS reactive forwarding and implemented a reactive forwarding outside of the core using the gRPC and Kafka event distribution system. It means that if you look at the current version of the reactive forwarding, so we receive the packet, extract the match fields, install flow rules, and return the packet back to the pipeline, right? So the same thing for the external reactive forwarding. So we use gRPC Kafka to externalize event processing, and then we use gRPC to return back the packet out to the pipeline. So, and that's it. Any questions, any comments?
Question, did you use per hop or did you use per hop reactive forwarding? So, because
for the
for your for your measurements, because clearly in production you would be best served to do the not per hop, right? Basically, control plane gets the copy of the packet only once from the first data path element, and then the rest of the way it goes through following the flow rules. But for the purposes of measurement, it might be better to visit every hop, so you have more samples.
Yeah, to be fair, because in the current version of ONOS, I implemented a optimized version of that as well. that typically we don't need to do it per hop. So
Right.
we can do it in the first switch that receives the packet. So install flow rules for the rest of the switches because we compute the shortest path and end-to-end path, right? So we can install flow rules for the rest of the switches. So the other switches don't send the packet to the controller.
Exactly.
So and then it reduces the response time significantly. But to be fair, with the current version of ONOS, so I did it per hop. So to make sure that the response time is completely fair with what we have in the current version of ONOS.
Great. This is not really a question, this is just more of a comment, because I think it was you and Professor Doug Comer, right?
Yeah.
You guys published a paper on ONOS in Register a few months back. Is that correct?
ONOS? Oh yeah. So the interview thing, right?
Right. Yeah.
Yeah.
And so it was really interesting because it was at the same time we were basically already starting on the micro ONOS journey.
Yeah.
Trying to disaggregate, and same observations that you guys made basically confirmed the observations we made on our side, and then some new ones too. So this is great.
Yeah, actually all of these things happened at the same time. So David Bimbridge presented a tool called OpenFlowT to externalize packet processing independent of the SDN controllers. But the idea OpenFlow is like a proxy, right? So it sits between the SDN controller and then externalized packet processing. So what I did is a kind of extension of that idea, but instead I just built in an application that does that. So it doesn't act like a proxy. So that means that if we would like to use it for OpenDaylight or other SDN controller, we need to implement another event distribution system that does the same thing.
Great, this is really interesting. Is there any other questions?
Yes. Yes. Actually, there are two repositories. One is the github.com DNOS project, DNOS project. So this is the gRPC event distribution system. So there is it has a website. It shows that how you can use it in different programming languages to implement a packet processor. So I did all of this stuff alone, so I don't have an army of programmers to maintain all of this stuff. So, but I think that if you have any question, you can ask me. There is another project, Umbrella project. So that also is an organization, Umbrella-project. So Umbrella project is intended to provide APIs independent of the SDN controllers. So that means that you can get these two pieces together and use them to implement those applications. These are two separate projects. Umbrella is just a use case of the event distribution system.
Okay, thanks.
So I can give you the links after that.
So thank you, Adib.
Thank you.
So I think we're ticking back on time.